right? The only place this n plus 1 appears is going to be here. So if this thing is n plus 1, this thing is n plus 1, then this here is going to be also be n plus 1. So the difference, you can modify, right, the temperature at index time n to n plus 1 simply by multiplying exponential minus alpha k squared delta t, right? And so therefore you can write this thing down as this, this thing here, that is still the temperature at the previous time multiplied by the additional n plus 1 term. So if you add 1 to that, you will have exponential minus alpha k squared delta t, right? And that's going to be equal to everything here is still just copied down, right? I'm just copying that down, okay? Plus
Yeah,
r.
like that's my question. Like I wrote on my note, like on your note in last lecture, you said that like t n plus 1 equals to tn times, like instead of delta t here, like uh, instead of like delta t, you wrote a delta n. So like I just confused about that.
Oh, it's possible. I might have made that mistake. Oh, it's
Okay.
definitely possible. Yeah, it's possible. Let me check. Did I? Yeah, it's possible. Definitely. I mean, yeah, yeah, definitely. I mean, it's very possible I make that mistake. Very definitely. Let me see. Where is it possible I made? Where did I make that mistake? Oh, I see. Yeah, I
Yeah,
kept
like right here.
thinking that. Yeah, that's right. That should be a delta. That should be a delta t. It should be a delta t. That's definitely should be a delta t. That should be a delta t. And where else did I? Oh yeah, this one. This one here should be a delta t. Yeah, that should be a delta t. There's no such thing as delta n. What the dirt am I thinking? Yeah, there's no such thing as delta n. That's a delta t, of course.
Okay, thank you.
No problem. I think where else did I make that mistake? Let me see. I think I'm okay there now. Yeah. Yeah. I think that should be fine. Yeah. Yeah. Good morning. And let me see, 11:44, right? And then this one's, of course, we still factor out. Let me just finish that out, right? So we just factor that out at n, and then this would be exponential. Um, the increment in delta x, so that's going to be I k delta x, right? Minus 2 plus, we need to subtract a delta x, so e to the minus I k delta x, right? So this is what we had done earlier.
So, Carlos,
Hello.
hi. I just want to clarify again how the alpha k squared and change in time and the I k change in x. What do those? How does that like translate down from the previous line? Like, can you just walk
Of course.
through that?
Yeah,
again?
yeah.
Okay.
Yeah,
I want to make sure
definitely.
I'm understanding it right. Thank
Yeah,
you.
so you notice, you know, you see this expression here, right?
Yeah.
And so, let's write them out fully, right? So I'll just write it down fully. So for example, tj at n, we said that that is exponential minus alpha k squared, our time increment n multiplied by delta t, exponential of not minus, but just I k j delta x, right? So if you were to write this thing down again, let's say at a different position, let's say, right? So let's say you wanted to write down j minus 1, let's say at n. Then you would write that down as, hey, I'm just going to replace it out, right? So as alpha k squared, you're going to have k squared n delta t exponential I k. And now at this juncture here, instead of having a j, you're going to have a j minus 1, right? So at this juncture, you're going to have a j minus 1 times delta x, right? And so if you look at that, you notice that this is minus alpha k squared and delta t exponential I k j, right? And remember, if you're adding and subtracting exponentials, that's the same as multiplying, right? So I k delta x negative, right? If you multiply exponentials, right, you're adding their powers, right? So I think this might be the key step, right? And at this juncture here, you'll notice that this expression here, that's the same as that expression there. And so what happens, therefore, you can write this down as Tj minus 1 at n is equal to Tj at n multiplied by this, what you might think of that as an offset, right? So exponential minus ik.
Okay. Thank you.
You see that?
Yeah.
And so it's exactly the same thing that you
Yeah.
do for when you have n plus 1.
Thanks for breaking that down.
Yeah, sum of powers is multiplication of two terms with the same base. Okay, it's 11:47. You know, there's the usual 74 people who are on, and you know, like I said, there was like 102 submissions for exam 2, and basically 1/4 of the class is not here. You know, it's just that's really quite remarkable. Yeah. Well, oh, wait a minute. You know, I thought it was 7. I thought I saw 75 there. It's actually, what happened? Why is that's really strange. About 10 people suddenly logged off. Is there like an internet problem, something here? We just suddenly lost. Yeah, people got disconnected and reconnected like in massive. So I think I just suddenly lost about 10 people, and then about 5 people reconnected back. Okay. Let me wait a bit. People are reconnecting back. I think about 10 people lost connection there momentarily. Okay. All right. They're getting back on now. That's good. All right. Let me see. Craig Nicholson. All right. Craig Nicholson. Where's the Craig Nicholson thing of a magic? Oh, there you are. Craig Nicholson. It's just WebEx being WebEx. Yeah. You know what's so interesting is just like as much as you guys might dislike, let's say, coding in Collaboratory or Python, you know, that kind of programming is ridiculously trivial, right? Because when you're doing this kind of coding, let's say for communications, something like WebEx, effectively, right? You are basically writing code because you have to understand when someone transmits data, right? Let's say I have this video feed of me or my talking, and I transmit this across a wire to you, to a central server or something like that. Transmission of information through the wire inherently gets corrupted with noise and error. It's impossible to send a signal without error. So a lot of the coding at the very core fundamental level on that coding has to deal with that random error. Okay. Imagine writing code where you have to be robust against random error, right? It's like, yeah, it's the rule of thumb is basically the more you know about coding and the more you know about technology, the more forgiving you are. So, it's like, and that's a characteristic. I think it's worth my 2 minutes here to spew this out. Okay. You know, the better you are as an engineer when you are, let's say, in a professional setting, you're working and things don't work. The better you are as an engineer, the more patient and forgiving you are when things don't work in terms of technology. And that's a character, that's kind of have to show. Um, yeah, that's, the best engineers recognize that, okay? And, you know, all right. Anyways, so let's take a look at the Crack Nicholson, this guy here. Okay. Do you see my pointer there? This guy. That is the Crack Nicholson. So that's where we ended up in the last class, right? So notice that this expression here that we also have here, then somebody has their headset on, their mic on, and there's something of a rubbing sound there. So, kindly either shut off that microphone or avoid, rubbing the microphone on it. Okay. Nat, did you wanted to write something on the annotations?
No, sorry. I'm on my phone because my computer is broken and I accidentally
Okay.
typed annotation buttons.
Yeah, no problem. But I may need to manually shut off somebody's microphone here because that rubbing sound is getting somewhat obnoxious there. Okay. Um, okay. Um, yeah. So at the end of the last class, right, I showed you the Crack-Nicholson approach to the finite differencing. This was what we did, and that's what we use to do the finite differencing. This is the naive way of doing the finite differencing. And we showed that this way of doing the finite differencing has a limit on what this R value can be, and it was 1/2. And because we have a limit, we have a constraint on what this R value should be, so that we have a stable algorithm. What happens is that for a given thermal diffusivity and for a given size of bar and the number of increments we want to divide it into, it sets a constraint on how big in time steps we can do. So essentially what that constraint is if R is constrained to 1/2, and let's say we desire to have some spacing, let's say 0.1. Let's say if our spacing is 0.1, then this is 0.01. Then if alpha is, let's say, is 1, the thermal diffusivity is 1, we get forced into taking time steps of 0.01 seconds, even though we have absolutely no desire, right, of getting how the temperature varies in 0.01 second increments. We are forced to take that kind of size, ridiculously small size of time increments, because otherwise our numerical algorithm is unstable and we just cannot get an answer. So we're forced to use very small time steps because of stability constraints. So no one would ever do it this way in real life. That's just not doable. Okay. And so what happens is another alternative approach is, notice that when we did this solving for the next time step, in calculating the finite differencing, we use the temperatures at the previous time step. Notice this is n plus 1. So a method that enables you to calculate the temperature at a later time step exclusively using information from the previous time step, that is referred to as an explicit method. So this is it's an explicit method, right? So what happens is in the Crack-Nicholson approach, right, they did the following. Actually, you know what? You guys completely cannot see my screen when I was doing that. You guys have to speak up, okay? All right. So, I was just nothing too crucial. I was just highlighting the differences of what we did earlier. So in the Craig-Nicholson approach, notice they're using U there instead of T. But let me write it down in terms of T, okay? Um, and so in the Craig-Nicholson approach, Craig-Nicholson approach, okay? What they did is the following. The, they for the time step, right? In time, right, at one position, right, over delta T, right? What they did is they're going to use an average, right? They're using an average of the second order finite difference at the previous time and at the following time, right? So earlier, right? Earlier we had something like this. We had t n j plus 1 minus 2, right? This was what we had earlier. Okay, this is what we had earlier. Okay, what Craig and Nicholson did was a very simple modification. All they did was say, let's take the average, right? So let's add the same second order finite difference, but let's do it at the current time, at a later time that we are interested in, n plus 1 minus tj minus 1 at n plus 1, divided by 2, right? So all Craig Nicholson said was, instead of calculating, right, your estimate for the second order finite difference with the delta x there, instead of just determining that from the previous time, let's also write that expression down for the next time that we want, for the next time increment that we want. So notice we are expressing that at the next time that you want, right? Exactly the same finite difference. And then take the average. There's your 2 there. You take the average. And that's it. Okay. And so what happens is that if we go off and write this out, it looks something like this. Okay, it's going to look like something like this. So tj n plus 1 minus tj at n. It's going to be equal to, you will have your r, right, divided by 2, okay, multiplied by tj n minus 2 tj n minus tj minus 1 at n, right? And then plus the other one there, tj n plus 1 minus 2 tj n plus 1 minus tj minus 1 n plus 1. And that's it, okay? But you notice at this juncture here, what happened to the delta t? Andrew? Well, that's how our r is defined, right? So remember, r is equal to alpha delta t over delta x squared. Yeah. So that this is r. So the delta t goes there, right? And then that's r divided by 2. Okay. So now you notice the Craig-Nicholson is going to be a bit somewhat more challenging, because remember, at the start, you know the temperature at every position, right? And you know the temperatures at time n. And you want to determine what are the temperatures at a later time n plus 1. So in fact, actually, all of these temperatures at a later time n plus 1, you don't know them. You know the temperatures at the current time n. You are solving for the temperatures at a later time n plus 1. So all of these values n plus 1, you don't know them. You need to solve for them. Okay? So let's collect our algebraic terms together and isolate all terms with n plus 1 on one side and all terms with just n on the other side, right? And so let's see how this thing would look like. So on this side, you're going to have, let's see what's going to happen here. Okay? Actually, let's do it this way, okay? So that we don't have to keep writing down this 2 down here, right? Let us instead define for our Craig-Nicholson, let's put down a 2 down there. So I don't have to keep writing down that 2, okay? And so if I make that modification there, then that thing is just R, okay? So we just don't have to keep writing down that divided by 2 over and over again, okay? So now you notice, let's see, which are the terms that have an n plus 1? Notice these are all n plus 1 terms, right? So let's collect all of these to that side. This term here, which has an n, let's move this to that side. So that's all we are doing, okay? So if we do that, let's see. There's that term, okay? So you have a minus r tj n plus 1, right? And then we have our current tj n plus 1. I'm sorry, this thing has a plus 1, right? This thing should be a plus 1 there, okay? I missed that, okay? And so let's move this term here with a negative 2 and combine it with that term. And so we will have plus 1 plus 2r, the temperature at J, n plus 1, right? And then we will have this term here, this one, I'm sorry, we will have this term here, okay? And that should be a plus. Why is this should be a plus, that should be a plus. That should be a plus, and that should be a plus. Okay? I made a typo there, okay? Not a typo, but a right-o, I guess, okay? And so we will have, from there, we will have a minus r, right? J minus 1, that's 1, okay? And then we will have the remaining terms on the other side, which is at the previous time, n, okay? So all of this will be equal to, now we write it down for the previous time, okay? So we will have r t j plus 1 n, and that is this term here, right? And then we will have, now the next one is, notice this term here will go to the other side, right? And combine with this one. And so we will have a plus 1 minus 2r, right? T at j, and then finally this last term here, right? So that's going to be plus r temperature at J minus 1 at the previous time n, okay? And so let me kind of box this out a bit, okay? Here. So that is the Crank-Nicolson equation that we need to solve, okay? So let me emphasize this. So we know the temperature profile at time is equal to 0. Let's say at n is equal to 0, we know the temperature profiles. So we know all of these values, these ones we know. And we want to increment to a later time, n plus 1. So all of these temperatures at a later time, n plus 1, you do not know. You see that? And so what happens is, how many unknowns do you have? Well, you have, how many k values do you have? You start from, let's say, if you have like 50 nodes, then you will have 50 nodes, then there'll be 50 temperatures you need to solve for at every time step. I'm not sure what's going on there, Owen. I'm not sure what's going on. Okay. So now at this point here, let's go off and let's do our stability analysis again, let's say. Okay? I'm not sure what's going on there. I keep getting kicked off and have to rejoin. Oh, I'm sorry to hear that, Kelly. Let me see. Who else is having that problem? You too, James? Okay. I'm so sorry that that's happening. Is it stable now, I guess? All right, let's, okay. So at this juncture here, let's go off and try out the stability analysis again, okay? So if we go off and do our stability analysis, let's see what happens, okay? So all of these terms, again, are just being offset by a TJ, right? So what happens is the easier thing to do is divide everything. So we will divide we will divide everything by tj n. So we divide across, okay? Divide across a tj, a t at some position j and at some time position n. We're going to divide across by that. Okay? So let's see what happens. Notice if you divide across by that, for this term here, what are you left with? So you're going to have a minus. So notice all of these terms on this side have an n plus 1, right? So what that means is we need to add on to that. We have to multiply it by an exponential that has that additional delta t term, right? So you're going to have minus, let me put out that thing outside. So you're going to have an exponential, right? I, k, not ik, alpha, right? Alpha k squared delta t, right? That is to account for this, the fact that we are incrementing one in a time, okay? Multiplied by, okay, let's see, minus r. Now, this particular term here is incremented in the wave number by 1, and so we will have exponential minus, not minus, but plus, right? We need to add on to it, okay? We need to add on to it k, j, delta x, right? Okay. Did I make a mistake there? That looks right. Let me see, rj and plus. That's correct. That's correct. Okay. Then, and then we have the next one here. So we have a plus 1 plus 2r. And then we have another one, which is minus this next term here, which gets shifted. This term here gets shifted by -1. Okay. So it's going to be r e to the minus k j delta x. Okay. Actually, there's no j. What am I talking about? What happens is it's going to be minus I k delta x. I k delta x with a negative sign. Okay. All right. And then on the other side, on this side here, it's equal to. Okay. Now notice all of these terms here, right? All of these terms are at the present time end, right? So the exponential minus alpha k squared, that term is already part of the tj, and that factors out. So all of these terms on this side only have the wave number correction, right? Okay. So let's put that in. So that's going to be equal to r exponential I k delta x, right? Okay. Plus this one here is 1 minus 2r, right? And then plus this last one there is going to be an r e to the minus I k delta x, because we shifted it by there is this, what's what happened there? So there is this -1 there. Okay. So let's see what happens next. Okay. So now things simplify down rather quickly here, right? Let's see what happens. Okay. So let's focus on that, right? Remember, that's going to be the growth factor, right? That's how much our solution will increase by. Actually, there should be a negative sign there too. Okay. So we have a e to the minus alpha k squared delta t, right? Multiplied by what? Okay. So let's see. So we're going to have a 1 plus 2r, right? Minus r multiplied by what? Notice this one here. Notice my iPad seems to frozen up. Let me that, okay. Okay. I appear to have lost something. let's see. Okay. So we will have a e to the minus alpha k squared delta t there, right? And then we are going to have this term, the 1 plus 2r, right? And then we will have a minus. Now you'll notice that this plus that, right? They're both negative, so you're adding them. So that will be a cosine. The sine part cancels out because this one has a negative there, right? So you're going to end up with a minus 2r cosine k delta x. Okay? And then on the other side, you're going to have something very similar. On the other side, you're going to have a 1 minus 2r, right? And then plus 2r cosine k delta x. Did you see? Okay. Are we together at this junction? Is everybody good with this? Okay. So let's see. We can do a bit more simplification. So e to the minus alpha k squared delta t, right? It's going to be equal to what? Now, if we look at this, there's a 2r there, right? So maybe we can factor that out, right? So we go something like, let's look at this one first. Okay, so that's going to be in the numerator. So it's going to be 1, and then we're going to have a 2r, right? And then we will have if we put a minus sign there, we'll have a 1 minus cosine k delta x, right? And then in the denominator, we have this one there, right? And so we will have a 1, let's say a plus 2r, 1 minus cosine k delta x. Did you see that? Can you repeat the cosines? Oh, definitely. Yeah. So, so for example, if you just, let's say this and that, if you're having difficulty with that. So, remember, e to the ix, e to the I k delta x. So that thing is equal to a cosine I k delta x. So that's Euler's formula, right? So that's going to be e. So that's going to be a cosine k delta x, right? Plus I sine k delta x, right? And the other one is if you have e to the minus I k delta x. If you look at Euler's formula again, so that's cosine k delta x plus I sine negative k delta x, right? But remember, I'm sorry, this is also a negative there, right? But remember, cosine is an even function and sine is an odd function, right? So that's also equal to cosine k delta x minus I sine k delta x, right? So sine negative theta is negative sine theta. Cosine negative theta is cosine theta, right? And so notice if you're adding these two together, as we are doing here, notice what we are doing is that we are adding this with that. We are adding together, right? So if we add these two together, so if you add these together, so that's going to be e I k delta x plus e minus I k delta x. If you're adding them, notice you're just left with 2 cosine k delta x. The imaginary part cancels out. Okay, Pat, get that? Okay. Okay, yeah, so that's all we are doing there, okay? And now at this juncture here, you look at this and you just say, hey, remember, right? This is the multiplicative factor that is multiplying the terms with the cosine and the sines, right? So if you look here at our solution, right? So if you look all the way back here at our solution, right? Notice it is this term here. Where's that? It is this term here, right? That is multiplying our terms of the cosine and sine. It is this term here, right? That is multiplying the exponentials at the previous solutions. So this term here, the absolute value of that has to stay below 1, so that if we keep multiplying and multiplying our temperature profiles by that, it's going to stay bounded. If that's more than 1, it will blow up to infinity eventually, right? So the requirement then, therefore, is that this term here, right, has to always be less than or equal to 1. Okay, what can you say? Well, yeah, obviously, it's going to always be less than 1. Why is that? Well, look at this, right? So if you look at that, what is that? That cannot exceed 1, right? That cannot be more than 1, right? This one here, that also cannot, I'm sorry, this thing is always a positive number, right? Okay, so this thing is between 0 and 2. This one here is between 0 and 2, right? So this can never go negative. This can never go negative. Our value of r is what? It's alpha delta t over delta x squared. Well, delta t is a positive number. And so r is always a positive number. So notice what you are doing there is you're subtracting a positive number from 1 and then adding that same positive number to 1. Well, of course, if this is positive and this is positive, you subtract from the numerator and you add to the denominator the same positive number, it will always be less than 1. And so what happens is that r can be any positive value, right? It can be any positive value. So if you do it using the Crank-Nicolson, you can have any value of r and it will be stable. Not necessarily accurate, but it will be stable. The solutions will not blow up, okay? So let's implement this and let's give this a try. Okay. After we have proven that it's going to be stable for any value of r, there is still actually a bit more to say about it. Copy. Let me drag this thing down. Okay. So when it comes time to actually implement this, there's a bit of thinking involved here. Okay, let's see. So notice what's going on here. Let's see if we were to draw this out a bit. Okay. I just realized I have been using it very zoomed in, so I'm gonna go back to 100% zoom so my pen is not too thin. Okay. So if you look at this, it goes like this, right? So if I were to write this out, let's say these are my temperatures at n+1. And these are my temperatures at the previous time n, right? Notice how it looks like. It's going to be a vector like this. It's equal to vector like this, right? Okay. So this will be the temperature at 0, temperature 1, temperature 2, temperature 3, and so forth. Okay. And then here you'll have the temperature 0, temperature 1, temperature 2, temperature 3, and so forth. But this is at n+1. This is at n+1, n+1, n+1. This thing is at the previous time n. Did you see it? And so you know the temperatures at the previous time at every position j, 0 to let's say how many steps you've divided your problem, right, spatially. So what you don't know is you don't know these ones you know. Okay? And let's take a look at our matrix, right? So we have our matrix here. Okay? Let's take a look. Okay, so notice we're going to have, right, for the first position, right? Actually, I need to it's easier for the eyes if I flip this equation around. Okay, so what I'm saying here is notice this is a +1 and this is a -1. I'm just going to put the -1 here and the +1 there. So I'm just rewriting exactly the same thing. It just looks easier on the eyes for the matrix. Okay? It's exactly the same expression, except I'm just flipping, writing one first before the other. Okay? So notice, right, that if we are at our leftmost position, right? So we're going to have a 1 + 2r there, right? And then we're going to have for the next term a -r and then a bunch of zeros. All of these are going to be zeros, right? Why is that? Well, let's take a look. Actually, this side here, let me not write it down yet, okay? There's a bit more to that side, okay? There's a bit more to that side. And so you notice how this thing's gonna work. We're gonna multiply 1 plus 2r by this, right? We're gonna multiply negative r by that, right? And all succeeding terms are 0 because you notice that at a particular temperature at position J, right? You're multiplying by 1 plus 2r and then subtracting from that the temperature at a position down. But notice there are no additional temperatures further down that affects that temperature at that node. Okay? So that's why all of these goes to 0. Okay? Now for the next diagonal element, next one is this term here. So when J is equal to 1, right? So for J is equal to 1, we have this one there. That's of our interest. We're going to have a 1 plus 2r there, right? And then this thing is for J is equal to 0. That's for J is equal to 1. That's for J is equal to 2, and so forth, right? So this 1 plus 2r is multiplying T1 and plus 1. So it's going to be this one. This was for J is equal to 1. But notice when J is 1, this one here is 0. So you need to incorporate that term. So you're going to have a minus r there. And then this temperature at J1 also depends on the temperature at J is 2. And so you need to add onto that the negative r times this temperature at 2. So you're going to have a minus r there. Okay? So what's going to happen is you're going to have a diagonal. You're going to have a diagonal on this matrix that is a 1 plus 2r. And then you're going to have another diagonal that is offset 1 above it over here of negative r. So you're going to have another diagonal of negative r's. And then down here at the lower end, you're going to have another diagonal of negative r's. So all of these are negative r. And then everywhere else is going to be 0. So that's how your matrix looks like. Now let's take a look on the other side. Okay? Now let's take a look at this side here. Okay? So notice if you look at the equations, on this side here, you have a bunch of these. You see, you have a bunch of these. But all of those things depend on the temperature at the previous time, which you know. So you can calculate that out immediately, right? Because those are the temperatures at the time n, which you know. Initially, time is 0. You know all of those temperatures. Okay? And so let's write it out. And so this this is for J is 1. You can write it out, right? So that's going to be R Tj minus 1 at n plus 1 minus 2R at Tj at n, and then plus R at Tj plus 1 at n. This whole term there, you know that, right? You know that. And then what's going to happen is all of these things all the way up to J is equal to n minus 1. All of these are all the same, right? You just write them all down. Not Jn minus 1, all the way to the one just before the last one. You know that, right? Okay. But notice, right? Notice that for the very first term, for J is 1, right? Notice for J is equal to 0 at the leftmost side. Look at what happens here. For the leftmost side expression, for J is equal to 0, you have this. What is that? Well, notice when J is 0, you still need to have the temperature to the left of it. Well, what is that? Well, that is the temperature that you have set your boundary to, right? So for this equation here, for this one here, right, we cannot write this down, right? Well, we could write it down. This thing is just the temperature at the left boundary, J is equal to. For J is 1, you subtract 1 to it, that will be the temperature at that boundary there, right? But we know that temperature at that boundary, right? So we're going to, we know what this is at J is 0 at the leftmost side. And so we can add this. So we add this value to both sides, and this goes over here, right? For the case of J is equal to 0 at the left side. So let's write it out. Okay? So we can write this out. So let's say, so R a t at 0 at n, right? No, I shouldn't write that. So that's going to be your 1 minus 2r temperature at J n. So let me write that down as 0, because that's just J is equal to 0. Right? Let me write this all out carefully. So you're going to have the r, right, at the left boundary, okay, at the left boundary, okay, to the n, right, plus 1 minus 2r, the temperature at J0 at n, right, plus r, right, T J plus 1. So that's going to be 1 to the right. Okay, so it's going to be T at 1 n. Okay, and then notice what happens is that this term here, right, when J is 0, we also know what that is at the left boundary. And so we need to add that to the other side too. Okay, so it's going to be a plus r, right, T at left n. Okay. Now, if you look at this for the rightmost boundary, can you explain where the matrix on the left came from? This matrix? Oh, certainly, yeah. So that matrix is coming from, let me zoom in a bit, okay? Maybe you can see it better. Okay. Okay. Let me see where that matrix is coming from. Let me explain. So what happens is that for, you see these J values there, right? Those J values range from 0 all the way out to however many nodes that you have divided your bar into, right? So each of those temperatures, you don't know what they are. You don't know the temperature. You don't know all of these temperatures for every single J value, going from 0 all the way to the number of increments that you have divided your bar into. Okay? So let's say J is equal to 0, J is equal to 1, J is equal to 2, right? Notice you can write this equation down for J is 1. You can write this equation down for J is equal to 2. You can write this equation down repeatedly for increasing values of J. And each J is representing a position on your bar. Does that make sense? So if you write this down, let's say for J is 1, right? So for when J is 1, then what is this? It's going to be minus R times the temperature above it, temperature to the left of it, T0, right? 1 plus 2R multiplied by the temperature at J is 1, which is this thing here, minus R times the temp for the next temperature. Right? There's your minus R. And then there's no other terms after that. So all the other temperatures, it's as if you're not including them. So they are all 0 afterwards. Okay? And so what happens is, if we keep writing this thing down, you notice that for each value of J, J is 2, J is 3, J is 4, it always depends on the temperature to the left of it and to the temperature to the right of it, but not any further, only the temperature adjacent to it. Okay? So the number of rows, no. The number of rows, no. So each one of these rows, each row represents one equation, right? And each of those equation, right, corresponds to the, you could think of that as a finite differencing at that particular position, J. Okay? Now, column-wise, notice you're going to be doing a matrix multiplication, right? So column-wise, the number of columns must match the number of temperatures that you have. So this A is going to be a square matrix. It's not arbitrary. So these are the coefficients. These are the coefficients, right? Simultaneous equations in it's like n equations in n unknowns, right? Are you guys with me, or I'm not sure? Are you guys understanding me? Jace, does this make sense to you?
I'm kind of following along a little bit. I get what you mean by like the terms to the right and the left for like the coefficient matrix, and I get what you mean by like increasing J values. But the matrix on the right, the equation, that's where.
Oh, on this side, on this side,
Right.
on the right side. So this is not a matrix. That's not a matrix. I'm just calculating that. It's an expression. It's not a matrix.
Oh, okay.
So, you see, so notice these are all processes. It's not a matrix, right? So on the right side, notice what you're doing on the right side. You have the temperature at these positions. You know this, you know that, you know this. Right?
Okay, so like with your top equation, that's like the 50 degrees that we had when we were doing the coding. Because that was like
are you referring to this topmost one? This one here?
Yeah.
Yeah, so that would be is that your head? Is that your mic here, Jace?
What?
There's this extremely loud feedback on my headphone.
Maybe.
Yeah, maybe. Okay, could you shut off the headphone for one moment?
Yeah.
Okay. All right. Yeah. So what happens is the temperature on the left, right? Notice for the very first row here, right? That is for J is equal to 0, right? Notice when J is equal to 0, right? That's our first node, right? What happens is when J is equal to 0, what is J minus 1? Well, that will be the temperature on the left side, on the left boundary, right? And you say what that is. Let's say, I think we set that to 50, let's say, right? And so when J is 0 and you want to go 1 to the left, well, that's the temperature at that boundary, which you happen to know, which is always constant. So that might be your 50 Celsius, right? Okay. And so you notice this term there, you know what that is for J is 0. But for when J is 1, J is 2, and so forth, well, you don't know what that is. It's only for when J is 0, well, you know what that temperature is. So you move that to the other side of the equation, right? And so that will reflect itself there. Okay? Now, what happens is also when J is 0, right, for any value of n, for some previous value of n, R, right? And likewise, even this temperature there, well, you also know what that is. This is to the left of J0, which is your boundary, right? So this appears there, and it also appears here because on this side of the equation, you're moving it to the other side. Okay? So now, how about at J is equal to the final and to the rightmost side, right? So to the rightmost side. So eventually you reach J equal to, let's say if you divide it into 50 increments, you eventually reach the last index, right? You reach the highest value of J, right? At the highest value of J. Once you reach the highest value of J, right? Notice you cannot go one more beyond that. You don't have to solve for it because you know what that is. That is going to be the temperature on the right side of the boundary, right? So I think in the problem, I think we set that to 85 Celsius, right? And so you know what this is, right? When J is equal to the highest, at the highest value of J, at the rightmost index. And so you can add this to this side of the equation because you know that value, right? And so what happens is for the last value of J, so for the final J, you still have all of these terms, right? And then you add onto it this term that's used to be on the left side because you know what it is. Okay? And so let's write it out. So this is going to be R Tj minus 1n plus 1 plus a minus 2R Tj at n, right? Plus R Tj plus 1n. And then plus again R Tj to to the right. Okay? And actually, j plus 1, I should have written this as right because there's no such thing as j plus 1 anymore once you are at the rightmost boundary. Okay? So actually, it ends up, you repeat that thing twice. Okay? But that's because on the left side of your equation, you have a term in which you are not solving for that. You're not solving for the temperature at j plus 1 when j is the lastmost. Instead, you're saying you know what that is, then you move it to the other side of your finite difference equation. Okay? So what you have here is essentially a set of several equations and several unknowns, right? So you might ask, how many equations, how many unknowns? Well, that is determined by the number of slices that you have made on your bar. So if you made a bar and you made 100 slices, then you have 100 equations, 100 unknowns. Okay? And you might ask, is that a big deal? I says, no, nothing. I mean, people solve these things up to like 1,000,000 unknowns, okay, easily, right? Let me see, Abdullah. So left and right boundaries are the temperature we started the ends of the bar from. Yeah, it's not that you started, you keep them the same, right? So remember, if you look at our problem here, right? If you look at this problem there, let me see, right? So notice this is going to be the temperature at the left side. This will be the temperature at the right side. They're always 50 and, is it 75? Oh, 80. They're always 50 and 80, right? So you know what those are. They're always 50 and they're always 80. Okay? And so there's no solving for tj 0 minus 1 or tj, the last value, 50 or 49 plus 1, because you know what they are. You set them. Okay? Okay. So let's do it. Let's do this thing. Okay. So now, before I get to that, let's take a look at our Wikipedia. Okay. And so this is essentially what they're doing, right? So given the terms on the right-hand side, you see this this expression here. So I just basically wrote out the matrix out for you, okay? And it goes something like, this is a tridiagonal pattern, meaning to say there's a diagonal, and then there's a few terms that's off to the one side of each diagonal, above and below the central diagonal, and then everything else is zero. So problems like this, as I said, in real life, in real engineering, you would solve these kinds of problems up to like 1,000,000 unknowns, 1,000,000 equations. That happens very often, real life problems. And so what happens is you do not, there's special algorithms for solving these kinds of sparse matrices in which most of the terms of the matrix are zero. Okay? So in this case here, we will be using in SciPy, they say something like a tridiagonal matrix algorithm, right? So in SciPy, SciPy has an even more general method for solving sparse matrices with sparse diagonals. And this thing is referred to as this. The SciPy linear algebra, we're going to solve a banded system. Okay, so that's what we're going to do. We need to solve a banded system. So let's take a look here. Okay, so I think this looking at an example is the easiest way to understand this. Okay, so if you look at this matrix there, you notice that, hey, it's only along the diagonals, right? So there is the central diagonal. This is the main diagonal, right? And notice above it, there's another diagonal. And then above it, there's another diagonal, right? And then below the main diagonal, if you go down by one, there is another diagonal there. Let me zoom in somewhere here. See if you can see. It's better if I zoom in, okay? And so what happens is you go off, right, and write the diagonal. So this diagonal that is 2 above the main diagonal, you write it down there, -1, -1, -1. Notice that above it, so if you were to extend this diagonal up, notice you'll have a 0 and a 0. They're empty. But actually, you can put any number in there. They're just ignored. So you just set them to 0, right? This other diagonal here, the 2, 2, 2, 2, well, above the 5, there's a 0 there, which is essentially ignored, right? So you go 0, 2, 2, 2, 2, 0, 0, -1, -1, -1. And then finally, along the main diagonal, you have 5, 4, 3, 2, 1, which is the main diagonal. And then there's the diagonal below it, the 1, 1, 1, 1. And then after that is a 0, or you just ignore it. And so you go 1, 1, 1, 1, and a star, they represent a 0, or they just don't look at that number at all. Okay, did you see? And so what happens is that the way you present this information to SciPy solve banded is the following. You go off, instead of creating the entire array like this, which is a 5 by 5 matrix, you only provided the diagonals. So notice this is the topmost diagonal, 0, 0, negative. That's the topmost diagonal, followed by the next diagonal, followed by the next diagonal, which happens to be the main diagonal, followed by, the final diagonal, the one that's below it. So you create an array in which the rows of the arrays have the values of the diagonal elements, right? Okay. The values that are outside of the diagonal, you just set them to 0, or they're just ignored actually. Okay. And so the way you solve it next is the following, and then you have your vector. So you have AX equals B. So B is the right-hand side of your matrix, your matrix unknowns, and the right-hand side, what you're solving for. This is your so-called AX is equal to B. So this is the right side. Okay. So you go like this. So you go solve banded, and then you see there's a 1 and a 2 there. What does that mean? So this 1 is saying how many diagonals are there below the main diagonal. So notice there's only one diagonal below the main diagonal. So that's what this 1 represents. And then there's this 2. What does that 2 represent? That 2 there represents how many diagonals are there above the main diagonal. So in that case, there's this diagonal and there's this diagonal. So there are 2 diagonals that are above the main diagonal. And then there's 1 diagonal that's below the main. So that's what this 1 and the 2 stand for. And then you provided your matrix that just contains the diagonals, where the rows are the diagonals. That's they call it AB, right? Followed by the vector that you want to solve for. Okay? So let's do this, okay? So if we are going to create our Crack-Nicholson diagonals, how do they look like? Well, it's actually pretty straightforward. What are our main diagonals? So there's the diagonal above it. Well, how should I call it? There's what should we call our diagonals? Maybe above. So D above, let's say. Yeah. So what is that going to be? It's going to be, if you look here, if you look there, our diagonal above is just negative R. Our diagonal below is just a negative R. So that it's going to be a 0. It's going to be a 0 followed by negative R. And this one here is going to be a negative R followed by a 0. And everything along the main diagonal is just 1 plus 2R. That's it, right? So let me put that in. Okay, so we can, we have the number of equations, number of unknowns, right? So we will just use, I think it's probably best to copy these down, and so we don't get confused. Let me make another copy of these down here, okay? Oh, it's 12:44 already. Time flies, my gosh, okay. Let me push this a little bit, and let me put that in, okay? And then next class, I will elaborate on this further, okay? So let's put in our diagonal above. So let me diagonal above, right? So what is that going to be? So it's just going to be, let's put in negative R, right? Times NP dot what? NP once. How many? The number of NX increments that we have made, right? I think I should stop here. Several of you have other things to do. So I'm going to stop here, and then we'll finish this off on Monday. Okay. If you have any questions, my pleasure to hang around and answer your questions. Okay. Hey, thank you, Andrew.
Thanks, Barbara.
Hey, take care. Bye-bye. Bye-bye. Thank you. If you have any questions, I'm happy to hang around and answer them. Hey, most welcome, Joe. Bye bye. Hey, have a good weekend. Yeah.